All right, so welcome to aerodynamic drag part 2. So in this example, or this video, we're going to take a look at an airfoil here and take a look at how that boundary layer develops around the airfoil. So try and understand a little bit more of the details of what's happening. So again, I'm going to draw my nice little streamlines coming off of here. And over the top surface, I'm going to draw my nice smooth streamline, hopefully. There we go. And over the bottom surface, I'm going to do the same thing. So here goes my streamline over there. And there we are. So I'm going to draw in zoomed in versions of the boundary layers here. And I'm going to assume that this wing that I'm taking a look at is relatively large. So let's think of it as maybe a larger aircraft, perhaps, or a medium-sized aircraft. And it's traveling relatively quickly. So in this case, what we might expect is that the flow will come in to the front of the airfoil and attach here to the airfoil. And at this point, it's going to go either above that point or below that point as it goes around the airfoil. And if we take a look at a given point, what we would expect to find is we would expect to find that the flow is sticking to the surface of the airfoil at that point. And it's gradually increasing in velocity, or rapidly increasing in velocity, more like it, as we go away from that point. So we would expect to see a velocity profile that looks something like this, such that out here you have the same speed, or the same flow speed, and then as we get closer to the wing, we have this rapidly changing flow speed. What we would expect close to the surface, or to the front surface of the wing, is that the layers of fluid, as they traverse down the wing, we would expect them to stay in a nice ordered sense, or in layers, right? So we would expect to see that if we saw a fluid particle entering one of these layers over here, we would expect that fluid particle to do a nice smooth trip through that region of the flow. And we're actually going to call this a laminar flow. So a laminar flow basically implies that the flow stays in these layers or laminars as it flows in whatever direction it's going. So here's our nice laminar flow. And really what it means is these particles that are in part of this flow are simply going to go in straight lines according to the velocity that they're hanging out in this boundary layer. So very nice, smooth, ordered, simple, clean-looking flow. What's going to happen is as we go further down the airfoil, we might actually encounter some roughness. So it could be that this wing has flown through some bugs recently, or it could be that the wing has some joints in it, or rivets in it, or other things in it. And those bumps are going to cause the flow that was going smoothly along here to actually go and experience a little bit of a perturbation. So you might find a little perturbation here. And depending on the nature of the flow, this perturbation might smooth back out like this, and it might smooth back out like this and turn back into laminar flow afterwards. Or if you get to a point where the surface imperfection or the velocity is great enough, what you might find is that the imperfection that you hit will actually start growing at a certain point. So in this case here, we hit an imperfection, and the imperfection, the perturbation due to the imperfection is going to cause that packet of fluid to move around a lot more and not be stable or not return to a laminar state. And if this starts happening, what we might expect is that these particles that we have here are going to start oscillating around a lot more. And when we see this happening, what we see is actually packets of flow that move upwards and downwards inside of that boundary layer. So if we come over here to our picture of how this looks on this side, let me just write laminar on top of this one. I'm going to write turbulent on top of this one, because that's what we're actually looking at here is a turbulent flow boundary layer. And in this case, what we're going to find is that the flow is going to, instead of being these nice straight lines, is actually going to be wiggly lines like this. And what we're going to find from this is that if we took a snapshot of that boundary layer at any given time, we might find something that looks like this. We might find that it looks kind of irregular and not very ordered, right? So these are the different particles here, and then this would be the velocity as a function of y. The same thing over here. This is the velocity as a function of y. If we extend this a little bit further, so I'm just going to erase this arrow here, and I'm going to say let's take a time average of that turbulent boundary layer. So let's take an average of lots of different snapshots, so maybe 1,000 different snapshots. What we might actually find from that snapshot of 1,000 different snapshots is, or the average of 1,000 different snapshots, is we might find that we get a much fuller looking boundary layer profile like this. So you can see the difference here in that I'm going to put the average velocity here. And the reason for this is that you get a fuller boundary layer down here, so you get more velocity profile down here, is because what we actually experience, and I'm going to put this in yellow kind of exchange packets here, is that you might find an exchange of fluid from the high fast moving momentum flow here to a lower momentum region here and vice versa, right? And this transfer of fluid between layers, right? So it's no longer laminar, so it no longer flows in these nice, beautiful layers of laminar flow. Because it's turbulent, you're actually exchanging packets of fluid with different energies. And these higher momentum packets will tend to drive the velocity closer to the wall to higher values. And the consequence of this, of course, is that the rate of velocity increase near the wall here, right? So dv dy is going to be greater in this turbulent flow than the rate of velocity increase in this case, dv dy. And as a result, the shear stress of a laminar flow is going to be less than the shear stress of a turbulent flow. So the region after which the flow transitions, so I'm going to just put yellow lines here, indicating essentially laminar flow over here, where we have nice ordered layered flow, or laminar boundary layer, I should say. Over here, we're going to have what's called a transition period, and this is the region where the instabilities that are introduced into the flow start to actually take hold and grow. And then down here, we actually have what's called the turbulent boundary layer, which is characteristic or characterized turbulent boundary layer. Let's actually finish that idea off first. It's actually characterized by this chaotic fluid motion between the upper and lower layers. And it really looks turbulent and chaotic, so it's disordered. And what we find is that the shear stress here goes up because of this rapid change in velocity with respect to height. Over here, the shear stress is lower because we have a relatively lower change in velocity versus height. On the bottom surface, you would see the same thing. So you would see a very similar behavior. You would actually see a laminar flow to begin, a transition period, and then turbulent flow back here in the boundary layer. So one of the goals of an aerodynamicist, or one of the goals of somebody looking at reducing drag around airfoils and streamlined bodies, is to try and design airfoils that push this transition region as far back as possible. So the idea behind those airfoils is you want to keep this flow in a favorable pressure gradient. So you want the flow, once it attaches to the wing and you get a boundary layer starting to form, you want the flow to be nice and gently pulled along the top of the airfoil. So in that regard, you want the pressure change along the length of the airfoil, so the pressure along this length of the airfoil, to gradually go to the lowest point and then gradually recover. So you want this to be gradual, and you also want it to be a favorable pressure gradient. So you want the pressure to actually decrease as you go along from the front to the back in a gradual manner. So let me just explain why that's the case, right? So if you have low pressure over here and you have high pressure at the front of the wing, and we know it's high pressure because the streamlines are actually curving away from the wing here. And if they're curving away from the wing, it means that the flow is pushing against those streamlines to make them go away from the airfoil. So this has high pressure pushing on those streamlines. And then up top here, we're pulling those streamlines back down, so it's low pressure, right? What's going to happen is this high pressure block of fluid is going to go, hey, this is awesome, there's a low pressure region up ahead. Let me head towards that. The challenge is if you have another higher pressure region back here, it's going to push on those particles. And therefore, when those particles see oscillations or it sees disturbances in the flow, we're actually going to find that those disturbances are more easily grown. So in terms of designing more laminar flow, we would want to tailor the pressure gradient with respect to the length of the wing in a certain way. The other thing we want to be aware of is the Reynolds number. And this is going to dictate whether we're going to most likely go to a turbulent flow or most likely stay in a laminar flow. So the Reynolds number is rho, so the density of the fluid, times the velocity of the fluid, or the characteristic velocity. So in this case, it would be U infinity, like this. And then in this case, we have a length scale, which I'm going to call the chord of the airfoil. And the chord here is measured from the tip of the airfoil to the back of the airfoil, or the trailing edge. That's going to be the length chord. And then on the denominator here, we have the viscosity at the bottom there. So here we have Reynolds number, and as the Reynolds number grows to higher and higher values, you're going to expect more and more turbulent flow happening in that boundary layer. So this is a quick overview of this idea of laminar versus turbulent boundary layers. You can actually do a lot of work in this area and actually read tons and tons of research papers on these topics. So turbulent boundary layers are still being studied today. Laminar boundary layers are much better understood and much easier to compute with a computer. So this region is well understood at this point for the most part. And then the transition region is also another region where we're still learning new things about it. So this idea of the boundary layer, laminar versus turbulent flow, Reynolds numbers, and as you increase the Reynolds number, you have more propensity for a turbulent flow. And then this idea of being able to design an airfoil to try and capture more laminar flow to reduce the skin friction drag, or this drag due to the shear stress acting on the surface due to the fluid, are all concepts we talked about in this video. So hopefully this makes a little bit of sense. We'll take a look at some of this and how this actually manifests on airfoils through some computer simulations. So hopefully we'll have some fun doing that. All right, thank you.